I'm sad I wasn't able to do these examples in class because I like the examples, but I want to make sure you at least had some background to do some of these tomorrow. So these are a couple sample problems. You can also go to the physics classroom reading on energy. They've got a bunch of the tutorial where we had the reading quiz before. They've got a bunch of practice problems, and they have brief solutions to the problems I'm assigning as well, which I'm putting a link in Schoology for that. Anyhow, here's sample problem number 1. We've got someone, an 80 kilogram student up here. They're attached to a bungee, and it's of 20 meters of unstretched length, and she wishes to lower herself and retrieve an orange that's landed on top of a bear trap. That's unsafe, but she needs to lower herself carefully to reach the orange without triggering the trap. And this is a 60-meter height above which she's going to lower herself. So the key is determining the spring constant needed for the bungee in order for this to happen. Now there are other real-life complications for this, which we can talk about in class, but here we just want to think about this. So first of all, if we think about how much we need the spring to stretch, the spring would actually need to stretch 40 meters since it's 20 meters long. If she has an 80 kilogram mass, you could either do 80 times 10 or 80 times 9.8 newtons per kilogram. That's the gravitational field strength constant on Earth. I use 9.8 here. I think I'd use 10 if I were you. So 80 times 9.8 is 784 newtons. 80 times 10 is 800 newtons. At any rate, so now I'm going to use the equation which we came up with, which is Hooke's law, and which we saw in lab as well. So that relates the stretch of a spring to the force acting on it. So 784 newtons is equal to K, that spring constant, multiplied by the stretch, which would be 40 meters. So the spring constant for this stretch is 19.6 meters, or newtons per meter, not that much different than some of the ones we used in class. So the next thing I want to do is I want to find the energy stored in the stretch bungee. So you could either do this graphically or mathematically. Mathematically, 1/2 K delta X squared. Graphically, you could do something like this. Make a plot, 784 newtons, 40 meters of stretch, make a triangle, area of the triangle, 1/2, height times base, 1/2 784 times 40, gives us that exact same answer. So I want you to understand you can solve things more than one way, since the area of force versus stretch graph does give us the elastic potential energy. Sample problem number 2, we've got a 50 kilogram chair which is pushed with 45 newtons of force, and the chair is moving at a constant speed. So this is going to be dealing with work, since work is a force applied across a displacement and the direction that force is applied. So it's moving at a constant speed. So assume that the chair is pushed for 20 meters. So finding the work done on the chair, this is FD, and it really shouldn't be F cross product D, it should be F dot D. Maybe I can make that a dot. Ugh. Sure. Maybe I'll move that up there. Yeah, F dot D. Sure, that's good. Which is FD cos theta. That's a dot product as opposed to a cross product. You may have heard about those in math. Anyhow, 45 newtons times 20 meters, 900 joules of work is done. So if the motion is completed in 10 seconds, what's the power? Well, 900 joules divided by 10 seconds is 90 joules per second. So that's 90 watts. Power is the rate at which energy is transferred, so you would have 90 joules per second or 90 watts. Part B is asking if work is done on the chair, yet the speed isn't increasing, what must be inferred about the situation? Probably that there's considerable friction. Now, if you assume that all friction is removed, determine the final speed of the chair. So essentially what we've got here is, if you think of that 900 joules of input, and it's going to be going to speeding the chair up, that's kinetic energy. And I should say, assuming the chair starts at rest, so let me type that in. Forrest. I'll make that purple also, so that way you'll never know that I screwed up. Sure, it looks just like my handwriting. Okay. So 900 joules of input. Energy input is going to equal the final energy. The type of final energy is kinetic. So I've got that 900 joules is now going to equal to 1/2 mv squared. So that says the chair will be moving 6 meters per second. That's about 20 feet per second. That's kind of fast. That's most of the way across the room in 1 second. So that would be kind of a dangerous thing. So anyhow, I hope those couple examples help. And again, there are solutions on the physics classroom to the problems that you're going to be assigned in class tomorrow. Thanks. I appreciate you working with each other. Bye.